Good morning, everyone. I'm Charlotte Deng. Today my topic is a comparison of gravitational effect between a spherical random ball and a spherical shell discretized using tesseroids. This presentation has 5 parts: introduction, theory, numerical experiments, conclusion, and outlook. Gravity field modeling due to mass distributions of the Earth is one of the fundamental issues in geodesy and geophysics. A spherical shell is a commonly used reference model among different mass bodies. The reason is that a spherical shell has analytical solutions and simple formulae for the gravitational effects and can provide reference values of the gravitational effects for the tesseroids in the numerical experiments. However, the computation time of a spherical shell discretized using tesseroid is known. The situation is worse, especially for the final grid size. In gravity field modeling, there is another reference model of a spherical zonal ball discretized using tesseroids for the evaluation of a different numerical method of a tesseroid. A spherical random ball also has the analytical solutions of the gravitational effect when the computation point is located along the polar axis. In terms of the quantity of discretized tesseroids, a spherical random ball is smaller than a spherical shell, and the corresponding calculation time will be largely reduced. In terms of spherical mass distributions, an important model is a spherical cap. The difference between two concentric spherical caps is the spherical random ball. Herein, the gravitational effects of a homogeneous spherical cap are derived. Firstly, the formula of the GP of a spherical cap is presented in equations 1 and 2 when the computation point is on the polar axis. Then, the expressions for the GV and the GGT of a spherical cap are derived in equations 3 to 7. Moreover, the formulae of the GC of a spherical cap are divided in equations 8 to 10. Regarding the gravitational effects of a spherical random ball, substituting the above equations of a spherical cap into equations 11 to 13, the expression for gravitational effects of a spherical random ball can be obtained. In a numerical experiment, the relative errors using tesseroids to discretize the whole spherical zonal ball and the spherical shell are performed by 3D Gauss-Legendre quadrature method. The numerical result of the comparison of the number and the computation time between a spherical random ball and the spherical shell discretized using tesseroids in double and quadruple planes with different grid size are listed in this table. It's interesting to find that the general ratio value in the first column is equal to 180 divided n, while n is from the general grid size. Furthermore, the computation time of a spherical random ball discretized using tesseroid is about 180 divided n times less than that of a spherical shell discretized using tesseroid for gravitational effect with different grid size in double and quadruple planes. Then, we investigated the comparison of computation errors between tesseroid discretized a spherical random ball and the tesseroid discretizing a spherical shell by focusing on the influence of computation point height on gravitational effect with different grid size. Numerical experiment reveals that the mean values of the relative appropriation errors in log-10 scale of the gravitational effects for spherical random ball discretized using tesseroids with different grid size are smaller than those for spherical shell discretized using tesseroids. Thus, it can be confirmed that the computation errors of a spherical random ball discretized using tesseroids are smaller than a spherical shell discretized using tesseroids. This study goes beyond the previous studies in that the simple analytical expression for the radial GV and the radial GGT of a homogeneously spherical cap and spherical runner bond are derived. Moreover, we derive the new analytical formulae of the GC of a homogeneously spherical cap and spherical runner bond. The numerical quantitative analysis of computation time and errors of the gravitational effects are carried out for the spherical runner bond and the spherical shear discretized using tesseroids with different grid size. Regarding the computation time and errors, the benefit of a spherical runner bond discretized using tesseroid is numerically confirmed in comparing with a spherical shear discretized using tesseroid. A spherical runner bond discretized using tesseroid can replace a spherical shear discretized using tesseroid in gravity field modeling in the future studies. Finally, this is the outlook. This is the reference. That's all. Thank you for your attention.